Hi everybody, this is Jade Xu at the University of Memphis. Today, using an example, we are going to learn how to conduct a repeated measure ANOVA in SPSS and read the output. Here is my example. So the researcher wants to study the effect of an anti-anxiety medication. A random sample of 7 participants were selected, and their anxiety level was measured on a scale from 1 to 10 before they started taking the medication, 1 week after they took the medication daily, and 2 weeks after they took the medication daily. Here, I entered the data into SPSS. Remember that every line is for one observation, and every column is for one collection of variables. So we have 3 trials. We collected data 3 times before 1 week and 2 week time. So they need to be entered in 3 different columns. To begin the analysis, we come to this place, Analyze, General Linear Model, then pick Repeated Measures. First, you are asked for the number of levels for whatever the reason the SPS called factor 1. That's actually asking you how many times the same measure was repeated taken. So we have 3 measures of anxiety level. Here we enter the number 3, then you click Add, and then you can give a name to a measure. You can call this, treatment conditions, you can call it times, you can call it trials. So I'm going to just call it time, and you can, at this point, click Define, and you have time 1, time 2, time 3. We know we have time 1, that's before, time 2 is week 1, time 3, that's week 2. So I'm going to bring them over. This is how I get my repeated measures here. Remember, we want to ask for descriptive statistics and estimate of effect size. Okay? Then just click OK when you're ready. And here is the output. The first table, very simple, just tells you that for your time as a measure, you have 3 repeated measures. It was taken, the measure was taken at 3 different times. And for each measure, for each time the anxiety is measured, you're given the mean and standard deviation within that particular trial. And we always have equal sample sizes because this is repeated measure ANOVA. If anyone dropped out, you will have to delete the individual's data from all repeated measures. For the purpose of our analysis, we can ignore this table. And this is the test of one of the assumptions for repeated measures ANOVA, sphericity. And we are not going to go to details about this test, but you need to know this is the information you're looking for. You want the sig, I always call this the p-value. You want the p-value greater than 0.05. If you fail to reject the null hypothesis, in this case, that means we met the assumption of sphericity. Okay. This table gave more information than what you need to know. 4 different tests about your null hypothesis were offered. You choose the right one depends on the structure of your data, whether you meet the sphericity and other factors that you need to consider. In our case, since we know we met the sphericity assumption, we can read the first line for both the factor and the error component. The sum square we have here for factor 1, this is actually the sum square of between treatment. Remember, we have 3 trials. That's why the degree of freedom is 3 less 1. We have 2. You divide the 2, you get the mean square for the between treatment. And how do we get the F value? We need to read the error component. Here, it's the residual sum square, 2.67. The degree of freedom, 12. The ratio between the two gave you 0.222. If you divide the sum square, the mean square of between treatment by the mean square of residual, you get the F observed. So the p-value is lower than 0.001. This tells us that if the null hypothesis were true, the null hypothesis says there's no difference in the anxiety level measured at the 3 times. If that null hypothesis were true, the probability for us to observe the 3 means with such a strong differences is lower than 0.001. Okay, and this partial eta squares indicate that about 97.4% of the total variance can be explained by the differences in the 3 trials, the 3 times the measure were taken. We don't need this table for now, and we do not have a independent variable, do not have a grouping variable that's put our subject or our participant into different groups. But in this table, you can also see what's the individual differences. This line gives you the part of within treatment sum scores that is due to systematic individual differences in the trials. So with information from the test of the within subject effect and the information from here, the last line, the test of between subject effect, you can summarize the test result into a table like this. Even though the SPSS does not straightforwardly offer you a table like this, you can do this yourself. We have between treatment type sum square, that's 98.667. Degree of freedom is 3 less 1 give you 2. The ratio between the 2 is your mean square. And the within treatment sum score is further partitioned into the between subject sum score, which is from this table right here. We have 7 subjects, so the 7 less 1 gave you a degree of freedom of 6. We copied the information from this line to our between subject line. And the residual information, the sum score, the degree of freedom, and the mean score, again, is from this test of within subject effect. We know that the sum of these two, 7.619 and 2.667, gave you the total within treatment sum score, and the sum of the between treatment sum of scores and the within treatment sum scores, those two add up, give you the total sum scores. Okay. The degree freedom, I gave you the formula, you can figure them out. The total degree freedom is 7 times 3, last 1. And we get the mean score for the between treatment, and we have the mean score for the residual. The ratio between the two is the observed F value, and the p-value and the eta squared, you can get them from the SPSS as well. So now we have a significant F test. We have a p-value that leads to the rejection of the null hypothesis. The conclusion is that we have significant difference in the anxiety levels measured at the 3 times. We're not done because we need to figure out what measure is different from what measure. So we need to do a post-hoc pairwise comparison. To do that, you can go back to SPSS. You go to the same place that you did your repeated measure ANOVA. In this place, all you need to do is ask for a comparison of means at this place called options. This is the factors that you want to compare, and you compare the mean effect, and just keep the default and click continue and OK. In addition to the old output we already have, here is a part that gave you the post-hoc test. The estimate marginal means have the means of the 3 trials, and this is the test of how strongly they differ from each other. So measure at time 1 before they take the medication versus time 2, 1 week after they take the medication. The difference is 1.429 on their measure of anxiety, which is statistically significant. So is the difference between before and week 2, and the difference is 5.143. That has a p-value lower than 0.001, so that is statistically significant. Between week 1 and week 2, the two means has a difference of 3.714. Again, the p-value is so low that we're going to reject the null hypothesis. Based on the pairwise comparisons, we conclude that the average level anxiety have significant differences between each of the 3 pairs. In other words, the anxiety level measured after 1 week of medication is significantly lower than before the participant took their medication, and the anxiety level at week 2 is significantly lower than the time before they start taking the medication, and also significantly lower than the level at which they took the medication for 1 week. So to answer the research question, yes, this new anti-anxiety medication is effective in reducing the patient's symptoms.